Okay, so Almedi Cherradi will tell us, sorry, because this is, okay, will tell us why and how every model category induces a derivator where in double categories. So please, the video can start.
Hello everyone, my name is Elmedi Cherradi, and today I'm going to present some joint work with my PhD advisor, Paul-André Méliès, titled Every Model Category Induces a Derivator Valued in Double Categories. So first, to set the background, given a category M with small limits, and given a functor U between small category, then we get a functor U star between the diagram categories associated to M, which admits a right adjoint functor noted for real U or U with a subscript star, which is defined by a right-can extension along the functor U. Now we can add homotopy to this setting. Just consider a model category M with a class of equivalence W. Then every functor between small category induces this time a precomposition functor between the homotopy categories, where we take the localization with respect to the pointwise weak equivalences between diagram. It now has right adjoint defined by homotopy right-can extension. This leads us to the notion of derivators. Derivators were introduced by Grothendieck to axiomatize the situation, starting from a two-functor, strict two-functor, from cat up, where 1, 2 means that both the morphism and the two cells direction are reversed, into K, which is a given two category with finite products. Historically, K is cat, the category of large categories. And note the action of this functor D on morphism U star. Such a strict functor D is called a prederivator. To get a left derivator from this, we need our prederivator to satisfy 4 axioms. The first axiom has to do with finite product. It says, first of all, that D of the coproduct is equivalent via the canonical map to the product of the D's. And moreover, the canonical map to the terminal object of K from D of the empty category is an equivalence. The second axiom has to do with detecting invertible two cells pointwise. Namely, given a small category A and an object X of K, and if we have a two cells phi such as in the following situation, so a two cell from F to G, it is invertible if and only if every whiskered two cell, such as this one, is invertible for every object A of the category A. The third axiom is just the statement that the functors U star admits a right adjoint for all U. And finally, the fourth axiom has to do with pointwise, the computation of pointwise scan extension, in fact. So it says that the natural transformation alpha that is induced by the slice category A on B, where U is a functor from A to B, so we have a canonical comma square such as this one. Then if we take its image by D, then we have a two-cell alpha star, which we require the mate of to be inversible. So the mate of alpha star is just this one. We will require it to be inversible in the two category K. This leads us to the important example of Quillen derivator. The starting point of our work is in fact the following key results due to Sizinski in 2003. The prederivator dm, which was defined on the slide about the homotopy covariance diagram, which is associated to a category, a model category M. This prederivator is a derivator. This is the theorem. So we deduce from this a simplicial object in CAD by just precomposing with the inclusion of the category of simplices delta with n-dimensional simplex noted n between brackets into cat. So this is two subcategory of cat. And we get this construction, which is inspired by hammer construction that is due to Dwyer and Kahn. Let us recall quickly the single condition. Given a simplicial object S in cat, for example, we have a canonical cone of this form, and we say that the simplicial object verifies the single condition if every such cone is a limiting cone in cat for every n larger than 1. Now we are able to state the main theorem of the paper. Suppose given a model category M and its simplicial object nerve M defined just as explained, then we have established that the simplicial object nerve M satisfies the single condition. The two ingredients of the proof, two main ingredients in the proof, in fact, are the following. First, we rely on the three-arrow calculus in the model category that reduces homotopy to the existence of 3x3 diagram of the shape below. This is discussed in great details in a book by Dreyer, Hirschhorn, Kahn, and Smith, 2004. And the second ingredient is a notion called equivalent bifibrations, which is introduced by Kahn and Méliès in 2020, and which enables us to connect by pull and push the various zigzags in the previous diagram in M, which represent the same morphism in the homotopy category. Now we may rephrase what we've just said like this. Suppose given a category K with finite limits, a simplicial object in K satisfies the single condition, saying that it satisfies the single condition is exactly the same thing as saying that it is an internal category. It defines an internal category in K. When K is the category of large category, we may call such an internal category a double category. We have thus obtained a double category in a canonical way that we will call double M from the model category M, which has horizontal arrow dimorphism in M, so before localization. The vertical arrows dimorphism in the homotopy category, therefore after localizing, and the double phase are related to the Hammock construction. Precisely, the double phase look like this. So the conceptual definition of those double cells is in fact morphism of D of 1, and we may see it as represented by those kind of diagrams. So this is a double cell associated from F to F prime with vertical components U and V. And of course, we take the right-hand side to be a diagram in M that we consider only up to an equivalence relation that is akin to the Hammock construction. We may now want to state, or rather to make the following observation. Given the simplicial object nerve M, in fact, it leads to a simplicial object in there, where there is the two category of derivator with pseudo-natural transformations and modifications. This follows from the nice result that shifting a derivator by a D by a small category, namely taking the following two functors dA, which associates to every small category B, D of A times B. This defines a two functor which satisfies the axioms of a derivator. We're now in the position to state the second main theorem of the paper. By applying this shift construction globally, so defining a two functor E that associate to every small category A the derivator dA, we have constructed a two functor that defines a derivator in the category there, so a derivator of derivator. The key ingredient of the proof this time is a calculus of exact square in cat. So we have established in particular that if we have two functors U and V in cat, then the following pullback square has induced is exact in the sense that the induced maze transformation is invertible. Finally, we might wrap up everything by saying that we have established that for every model category M, the previous derivator of derivator restricts to a derivator of double categories from the two category D up into double cat, where really is the full two subcategory of really categories in cat, and double cat is the two category of double categories, so seen as simplicial objects satisfying the single condition, through the double functors and modifications. And this gives the name for this presentation. Thank you for your attention, and I may leave you with the reference. Thank you again.
Maybe have the time to tell in the pre-recorded video. Maybe not everyone was familiar with, or maybe probably not everyone was familiar with the notion of derivator, because it's been mainly studied in France, I think. It was influenced by Grothendieck, and despite this fact that it's not well known, we really believe it's a key ingredient to making computations and computing homotopy limits, co-limits, and more generally homotopy can extensions. And it will prove, in our opinion, useful to produce or some interpretation of homotopy type theory. So this is currently something that we're working on, and this can explain or motivate why we had such an interest for this construction of a double category, like the whole study of the derivator associated to a model category, and the interesting double category that it allows us to construct. So maybe this was the first comment. If any of you have a question, I would be glad to answer it.
There's a question. I'm bringing in the microphone.
Thanks for the talk. I have a question. So you basically extract a two-dimensional structure out of a model category. You get a double category out of this model category. Another way I can think of doing this is if you take your model category, you think of it as being an infinity category, and you extract from that a 2-1 category just by truncating locally the Ohm spaces. Do you know how the two things are related? They seem to contain pretty much the same data, but I'd like to hear your take on this.
Yes, to be completely honest, we did not investigate the exact connection with the Bauer-Steele localization and things like that, but it boils down to a similar idea that there should be a connection, or rather a way to connect kind of morphism inside your infinity category with well, the model category that presents it, for instance. But we are not investigated. We have not investigated further this question, and probably we will be getting some interest for this, because it's a question that arises quite naturally indeed.
Any other question from this room, from the other room, or from the Zoom? If not, let me thank the speaker again.